So my name is Frank Lemoine. I'm chair of the International DORIS Service, and the reason you are watching a recorded presentation at this meeting of GGOS Days is that none of the members who are authors of this paper could travel to Rio de Janeiro to make this presentation. So we are recording this presentation with the assistance of the video services at the NASA Goddard Space Flight Center. The purpose of this presentation that I'm making is to present you an update on the DORIS system and the International DORIS Service. And I intend to present to you some new information and clarifications on some points regarding the DORIS system. So I'm going to present to you first an update on the DORIS system. So just to remind you what DORIS is, DORIS, the acronym stands for, in English, Doppler Orbitography and Radio Positioning Integrated by Satellite. And these are the translations courtesy of Monsieur Google in Spanish and Portuguese, so I hope they're correct. DORIS is a French civil tracking system designed for precise orbit determination. It's for high accuracy ground positioning of beacons and for high accuracy orbit determination of low Earth orbiting satellites. The present performance is 6 to 9 millimeters RMS radial orbit accuracy as measured by independent high elevation satellite laser ranging data. It's an uplink and centralized system based on measurement of Doppler shifts of RF signals transmitted by a worldwide network of beacons. It was developed by the French Space Agency and in partnership with the French Survey and Mapping Agency, IGN, and the Space Geodesy Research Institute, the GGOS. So the system is composed of a network of stations around the globe. The satellite receivers can receive up to seven stations simultaneously. This is the DGXX receiver. And it consists of a control system that receives the DORIS measurements from each satellite every orbit. There are two frequencies, 2.036 gigahertz and 401.25 megahertz. It's a dual frequency system, which of course allows for correcting the ionosphere delay. The precision is 0.3 millimeters per second, and that's based on an ultra-stable oscillator that has a stability in terms of Allen deviation, delta F over F, of a few parts in 10 to the minus 13. The signal is free, and there's no limitation on the number of satellites that can carry DORIS receivers. So on the left, you see the current DORIS dual frequency instrument, the DGXX package, which is carried on the current satellites that are in orbit. It includes a redundancy of the ultra-stable oscillators and a diode near real-time orbit determination system, basically a very advanced Kalman filter that can produce 3.5 centimeter RMS radial orbit accuracy in real time. The provider is Thales Systems. The system has an excellent availability on the Jason-2 mission, which has just ended. After 11 years, the DORIS system was continuously available. The Jason-2 mission ended because of problems with the solar array and the spacecraft gyros, not because of any of the tracking systems, including DORIS. So there are three types of beacons in the DORIS network. The first is the standard beacon, which is known as an orbitography beacon. The second class of beacon is called a time beacon, and these are beacons that are connected to atomic clocks, and their purpose is to transfer the TAI up to the DORIS spacecraft. And then there's a master beacon, which also relays information. I'd like to clarify some of the nomenclature regarding what a DORIS station is, because sometimes I think there's a little bit of confusion. So a DORIS station consists of all the equipment at a DORIS site. That includes the transmission and management units, the ultra-stable oscillator on the ground, the backup supply system, the antenna, and accessories, and sometimes a weather station. The DORIS beacon is actually the unit which produces the transmitted signal. It includes the ultra-stable oscillator, and it generates the DORIS signal, which is sent via the cables up to the DORIS antenna. The DORIS antenna transmits the DORIS signals. That's depicted here on the left. And it's the precise orbit determination that determines the coordinates of the reference point of the antenna while taking into account the antenna phase variations, which are determined from measurements in an anechoic chamber. This is a bit of an eye chart, but it lists the DORIS-equipped satellites that have flown or are flying. There are 14 missions that have contributed to the International DORIS Service since 1990. 8 missions are now decommissioned or over, and there are 6 DORIS satellites currently in orbit. The orbits include polar orbits, generally sun-synchronous, and then the TOPEX-adjacent orbits around 66 degrees inclination. And the altitude range is between 700 and 1336 kilometers. The mission with the most longevity is the SPOT 2 mission, which was launched in 1990, and it continued in operation until 2009. Of course, I'm biased, but I think the most important missions are the missions that are dedicated to the measurement of global mean sea level, and those are TOPEX Poseidon, JASON 1, JASON 2, and now JASON 3. So this gives you sort of a visual summary of the time span of the different missions. In sort of magenta are the missions that have flown. So these include the SPOT satellites, ENVISAT, JASONs 1 and 2. The current missions that are on orbit, that includes Cryosat-2, HY-2A, SORAL, Sentinel-3A, and Sentinel-3B. And then future missions that will launch in the near future and into the 2020s. So in the near future, we have the launch of the Chinese satellite HY-2C, which will carry a DORIS receiver. And next year in November, approximately a year from now, we will have the continuation of the JASON 3 mission, which is the Sentinel-6 JASON CS satellite. This gives you a depiction of the geographical distribution of the DORIS network. There are approximately, as I said, 60 beacons around the world. The distribution is homogeneous between both hemispheres, and the DORIS team at the CNES and at the IGN have worked very hard to achieve this distribution, but it's also due to the cooperation and dedication of the many host agencies that have contributed to the system over the years. So the DORIS system is managed by a single entity. It has typical stations have a very long time series, on the order of 21 years on average. The network availability hovers around 90%. And that's because at any given time, there will be a few stations that are out of service. And because of the remote locations, it can take time to service stations that have minor problems. Half of the stations are located on islands or in coastal areas, and there's a good north-south distribution. 48 of 59 stations are co-located with other techniques. That includes GNSS, satellite laser ranging, and VLBI. I'd also point out that there are 28 stations that are co-located with tide gauges relatively close by. Now I'd like to review the 3 types of monumentation that we have in the DORIS network. And for more detailed information, I can refer you to this paper by Jérôme Saunier, which was published in Advances in Space Research in 2016. So the Type 1 monument is a tower placed on a load-bearing pillar of a building. This particular choice provides good sky clearance visibility and access to power when other options are not available. The Type 2 monument is a stainless steel tripod installed on a 1.5 meter high concrete pillar. And the concrete pillar is always appropriately anchored into the ground, into bedrock, for example, if it's there, with steel rebars, or into soil 1 to 2.5 meters with a deep foundation. And this is an example of an installation on Ascension Island. The Type 3 is a rigid steel tower installed on a concrete block that's compliant with stability requirements for pillars. This monument gives you a slightly higher ground clearance than Type 2, and it's used to provide sufficient sky clearance at a particular site. In the lower right-hand side of the figure, you can see a depiction of how that ground monument looks like underground. So the concrete pillar extends 1 to 1.5 meters into the soil, and then there's a concrete slab foundation that's also present. And we believe this is a very stable type of monument. So if you would like more information on this monumentation, there's a document on the DORIS website authored by Jérôme Saunier that describes this in detail. So I'd like to discuss now some of the improvements that are underway in the DORIS system. The first improvement that's been underway now for several years is the implementation and installation of the Type C Starrick antennas. The Type C Starrick antenna controls the location of the 2 gigahertz phase center to 1 millimeter. The early generations of that antenna only controlled the location of the phase center to several millimeters. The deployment of these Type C antennas started in 2014. There are about 18 stations currently equipped, and probably on the order of 10 to 12 will have a time series of 2 to 2.5 years that will be sufficient for being included in ITRF 2020. The second implementation that's underway is the 4th generation beacon, and it has updated electronic components. The most important attribute is that it allows the DORIS antenna to be up to 50 meters away from the DORIS beacon or electronic equipment. And the whole purpose of this is to allow a better viewing environment for the DORIS antenna. One of the stringent requirements that the DORIS team works very hard to achieve is to have sky visibility down to 8 degrees elevation and as few encumbrances or disturbances in the field of view to avoid disturbances in the DORIS signal. So I'd like to comment on the positive impact of the GGOS project. There are many countries that have responded to the call to build the core network infrastructure, and as a result of this, DORIS has moved to the Wetzel Observatory in Germany, which is now a 4-technique site. DORIS was installed in San Juan in 2018, and the DORIS site at Nyalesund was renovated in 2018. There are also plans to install DORIS, of course, at the Tahiti Geodetic Observatory at the site called Papanu, and that will be in cooperation with NASA, and that will occur sometime in the 2020s. There is a synergy between the different techniques, and there have been detailed studies between the DORIS and VLBI teams to see how the two techniques can cohabit together. And as a result of these GGOS efforts, the DORIS team has put together a ground antenna characterization of the error to develop an error budget that was published by Jérôme Saunier, and a detailed assessment of the stability of the DORIS network documentation. So this slide lists the DORIS stations in the southern part of the Western Hemisphere. The site with the longest time history and longest occupation is Rio Grande, installed in December 1987 in southern Argentina, followed by Arequipa and Cachoeira, Arequipa in Peru and Cachoeira in Brazil. Arequipa, of course, is a site that has co-located with the satellite laser ranging. So this chart shows the visibility circles at 800 kilometers altitude. So it's how the different satellites can see the DORIS signal. And there's good coverage over South America and into the Eastern Pacific and the Western Atlantic. We are working with colleagues in Chile to update the DORIS station on Easter Island. So to summarize, the DORIS system has been operational since 1990. In February 2020, we will celebrate the 30th anniversary of the DORIS system, of the first measurement on Spot 2. There are 59 ground stations. The 4G beacon is being deployed, and the new satellites will include JASON-CS, Sentinel-6A, as I mentioned previously, the joint NASA-CNES mission, SWAT, and the HY-2C and 2D missions scheduled for launch in the near future. So I'd like to give you a brief summary now of the IDS products. So first of all, we produce SINEX files, series of station coordinate solutions of Earth orientation and station coordinates. This is updated quarterly. These are weekly solutions. We provide reference frame solutions, which are position and velocity solutions. That's a cumulative solution that's developed over the entire time series up until the recent time, and that's developed bi-yearly. We have solutions for Geocenter. There's actually a pilot project that's underway to provide refined estimates of Geocenter, and the CNES Associate Analysis Center produces precise orbits which are distributed on a routine basis. So there's a rich source of information for DORIS at the DORIS website that includes presentations, reports, technical information, and extensive bibliography. If you're interested in the different technical aspects of the DORIS system, you can sign up for different electronic mailing lists. There is a YouTube channel, but the YouTube channel has information on the different attitude laws of the DORIS system, and there's detailed information on the characteristics of the different satellites that make up the system. We also have an annual activity report, which you can subscribe to or you can view on the web. And if you're interested, we encourage you to subscribe to our DORIS newsletter, which is published several times a year. So to summarize, the International DORIS Service has been a service of the International Association of Geodesy since 2003. We have 6 active analysis centers, 4 associate analysis centers, and that includes DGFI TUM, Technical University of Munich, which was just approved as an AAC about a month ago. We have 2 data centers, the NASA CDDIS and IGN. We have a combination center, an analysis working group, and different working groups working on different topics. So the current activities include the data processing for ITRF 2020. We are also looking at the near real-time delivery of DORIS RINEX and diode orbits that will start with JASON-3 in early 2020. You should contact Denise Detmering at DGFI TUM or Pascal Ferrage at the CNES for more information. There will be a call for proposals for an IDS station sometime in early 2020. What is an IDS station? It's a station that's dedicated for scientific purposes, and there have been a few of these over the years, but we are looking to initiate a call for proposals early in 2020. We are planning for an IDS school, which will discuss the DORIS technique and DORIS products. Planning is underway, so you should look for updates again early next year. And we have several working groups that you might be interested in joining. Alexandre Coer of the CNES is working on a pilot project for determination of geocenter from DORIS data, and you should contact him for more information. We're also working to make precise orbit determination software available with documentation so new analysis centers can join the IDS more easily. As many are aware, it shouldn't be a prerequisite for someone to write their own orbit determination program in order to join IDS. And finally, we have meetings next year that includes the analysis working group meeting, which will be in the spring, and the IDS workshop, which will be held in the fall 2020. That will be in Venice, Italy, associated with the annual meeting of the Ocean Surface Topography Science Team meeting. So, muy obrigado, muchas gracias. Thank you for your attention. I hope you have a productive meeting at GGOS Days. And if for further information about DORIS and IDS, please contact the IDS Central Bureau, the Director of the Central Bureau, Laurent Soudarin, Jérôme Saunier, the Network Manager, or myself as IGS Chair. Thank you for your attention.